in shallow seas that stretch beyond any horizon, where the water holds the faint metallic taste of dissolved iron and the air above shimmers with methane hazes, something stirs, not wind, not current, but the first whisper of a chemical revolution that will rewrite the very composition of Earth's envelope of gases. The world is 2.5 billion years younger than today, and its atmosphere breathes with methane and hydrogen sulfide, with ammonia and water vapour, with carbon monoxide and traces of noble gases, but no free oxygen, none at all. The sky itself would be toxic to nearly every form of life that will eventually call this planet home. Yet beneath these alien heavens, in the warm shallows where sunlight penetrates the clearest water and illuminates the sandy bottom, a quiet transformation begins that will echo through geological time. The ancient sun burns with perhaps 80% of its current brightness, casting a dimmer light across waters that have never reflected the blue wavelengths that oxygen will one day scatter through the atmosphere. Instead, these seas appear darker, more metallic, tinted with the dissolved minerals that flow from volcanic vents and primitive continental weathering. The temperature hovers in ranges that would feel tropical to modern sensibilities, kept warm not by carbon dioxide as in later greenhouse periods, but by methane, a greenhouse gas 30 times more potent than the carbon dioxide that future civilizations will worry about. Mats of blue-green bacteria, cyanobacteria, cluster in thin films across the seafloor, their surfaces slick and dark beneath the hazy atmosphere. They are Earth's newest inventors, though they know nothing of invention, having discovered through the patient work of evolution and chemical accident how to split water molecules and harvest sunlight in a way no organism has managed before in the planet's long history. These microscopic pioneers have evolved a molecular machinery so complex that modern scientists still struggle to fully understand its intricacies, a photosystem that can extract electrons from water molecules, the most chemically stable compound on Earth's surface. The process appears deceptively simple when written as a chemical equation: water plus carbon dioxide plus light equals sugar and oxygen. 6 molecules of water and 6 of carbon dioxide, touched by photons from that younger sun, yield 1 molecule of sugar and 6 of oxygen gas. The chemistry is elegant in its precision, revolutionary in its implications, and utterly routine to the bacteria that perform it trillions of times each second across countless cells. Each reaction requires the precise coordination of hundreds of proteins, the management of electron transport chains, and the careful balance of energy capture and storage. It is, by any measure, one of the most sophisticated chemical processes ever evolved on Earth. Only the oxygen part represents something genuinely new under this ancient sun, something that will prove more transformative than the sugar that feeds the bacteria themselves. For 2 billion years, Earth's atmosphere has been what chemists call a reducing environment rich in methane, hydrogen, carbon monoxide, and traces of noble gases but containing no free oxygen molecules floating loose in the air. The very concept of oxygen existing unbound, available to react with whatever it encounters, would have spelled death to most life forms that have evolved and vanished in the deep ocean trenches and hydrothermal vents where Earth's earliest biology took root. Anaerobic life has ruled unchallenged since the first primitive cells emerged from the chemical soup of early Earth, thriving not just in the absence of oxygen, but requiring its absence for survival. These organisms have evolved intricate metabolisms that harvest energy from sulfur compounds, ferment organic molecules into simpler forms, and extract chemical energy from the gradients between different environments. Some breathe sulfate instead of oxygen. reducing it to hydrogen sulfide that bubbles up through the water column. Others consume methane, breaking down the greenhouse gas that keeps their world warm. None of them breathe in any sense that later life would recognize. None of them require the gas that will become essential to nearly every complex organism that follows. Yet these bacterial mats continue their patient work, indifferent to the magnitude of change they herald, unaware that they are engineering the most significant atmospheric transformation in planetary history. Each cell splits water molecules with mechanical precision, a process that requires more energy than almost any other biological reaction, releasing tiny bubbles that rise through the water column like ascending prayers. The bubbles are so small they barely disturb the water's surface tension, yet each one carries 2 atoms of oxygen bound together in a molecule that will prove both destroyer and creator in the geological ages ahead. The oxygen dissolves readily into seawater, beginning a chemical conversation between life and planet that has never occurred before in Earth's 4.6 billion year history. Unlike the gases that dominated the ancient atmosphere, oxygen is promiscuous in its chemical behavior, eager to react with metals, minerals, and organic compounds. It seeks out iron dissolved in the seawater, forming the first rust particles that will eventually settle onto the ocean floor in distinctive layers. It reacts with methane in the upper atmosphere, breaking down the greenhouse gas that has kept the planet warm. It transforms the chemistry of weathering on the primitive continents, accelerating the breakdown of rocks and the release of new minerals into the ocean system. The bacterial colonies spread slowly across the continental margins, following the edges where shallow water meets the infant continents and creating vast underwater prairies of photosynthetic life. These early land masses bear no resemblance to the green and brown territories of later Earth. They are bare rock and sediment, sculpted only by wind and water and the endless patient work of geological processes, untouched by root or leaf or any form of terrestrial life. Volcanic activity still shapes their surfaces, building mountain ranges and rift valleys that will be ground down by weathering long before the first plants colonize dry land. The bacteria care nothing for the sterile landscapes above the waterline. They require only sunlight, water, and dissolved carbon dioxide, all of which the ancient oceans provide in abundance. Their mats grow thicker with each passing century, layering themselves in dense, leathery films that trap sediment particles and create the first substantial biological structures on Earth's surface. These living carpets can stretch for hundreds of kilometers along favorable coastlines, forming underwater meadows that represent the planet's first ecosystems large enough to be visible from space, if there had been any eyes in space to see them. The irony settles softly over the ancient seas, as quiet and pervasive as morning mist the gas that will one day power the flight of eagles, and the thoughts of philosophers, the metabolism of whales, and the cellular respiration of every breathing thing on Earth, begins its planetary career as waste, pure biological refuse, no more intended than the carbon dioxide humans exhale or the methane released by decomposing matter in swamps and landfills. The cyanobacteria care nothing for their revolutionary byproduct, show no awareness that they are fundamentally altering their world's chemistry. They photosynthesize because they must, because the chemistry of their cells demands it, because this is what evolution has shaped them to do over countless generations of mutation and natural selection. Their survival depends entirely on sugar production, on capturing solar energy and storing it in chemical bonds that can power their cellular machinery. The oxygen is merely what happens to be left over after they strip electrons and hydrogen from water molecules, a molecular afterthought that bubbles away into the surrounding water like smoke from a fire or steam from boiling water. They might as well be producing nitrogen or argon for all the biological purpose it serves them. Yet this waste product will reshape continents, freeze oceans, drive the greatest mass extinction in planetary history, and eventually enable the evolution of complex life forms that depend on oxygen as completely as the first anaerobes depended on its absence. Only Earth itself seems to notice the change, recording the evidence in chemical signatures that will persist for billions of years. As the first traces of oxygen begin to dissolve into seawater that has never known such chemistry before, the planet's mineral systems respond with the slow inevitability of geological time. The iron dissolved in these ancient oceans, present in concentrations far higher than in modern seawater, begins to react with the oxygen in predictable chemical combinations. Iron and oxygen possess an almost magnetic attraction for each other, their electron structures complementary in ways that make their union nearly irresistible under the right conditions. The marriage of iron and oxygen unfolds in the deep waters with a patience that only geological processes possess, a courtship measured not in moments, but in millennia. Dissolved iron, invisible in the ancient seawater, encounters the newly released oxygen molecules and begins the slow dance of oxidation that will paint the ocean floors in bands of rust-red sediment. This is Earth's first experience with widespread oxidation, the first time in planetary history that metals have encountered free oxygen in significant quantities, and the chemical response reshapes the very architecture of the seafloor. Iron atoms, stripped of their electrons by oxygen's relentless chemical appetite, precipitate out of solution as iron oxides rust in its most fundamental form. The particles are microscopic at first, invisible specks of reddish mineral matter that drift through the water column like atomic snow. But as oxygen production increases and more iron encounters its chemical partner, these particles accumulate into visible clouds, then settle into layers, then compact into the distinctive banded formations that will become one of geology's most reliable signatures of this ancient atmospheric revolution. The process occurs with mechanical precision across vast stretches of ocean floor in the deeper waters where oxygen concentrations remain lower. Dissolved iron persists in higher concentrations, creating a chemical gradient that drives the formation of alternating bands. When oxygen-rich waters mix with iron-rich depths, precipitation occurs in pulses, creating the rhythmic layering that geologists call banded iron formations. Dark layers rich in iron alternate with lighter layers dominated by silica, creating a striped pattern that records the ebb and flow of oxygen production like tree rings record the passage of seasons. These formations will eventually become some of Earth's most economically valuable deposits, the source of iron ore that will fuel the industrial development of future civilizations. The ancient bacteria, processing sunlight and carbon dioxide in their endless photosynthetic cycles, are unknowingly laying down the mineral wealth that will power steel production, automobile manufacturing, and skyscraper construction billions of years in the future. Only a planet could manage such profound irony, primitive life forms, preparing the materials for technologies they cannot possibly imagine. The banded iron formations spread across the ocean basins with the inexorable logic of chemistry. Where cyanobacterial mats flourish, oxygen production increases, and iron precipitation accelerates. Where the mats thin or disappear, oxygen levels drop, and different minerals dominate the sedimentary record. The result is a three-dimensional map of ancient biological activity, preserved in stone and readable by scientists equipped with the right tools and sufficient patience to decode the chemical messages locked in billion-year-old rocks. Modern geologists estimate that these formations contain trillions of tons of iron, representing the removal of vast quantities of dissolved metals from the ancient oceans. The process required millions of years to reach completion. As the bacterial mats slowly but steadily increased their oxygen output, and the ocean's iron reserves gradually precipitated onto the seafloor, each layer records not just the presence of oxygen, but its quantity, its seasonal variations, and the complex interplay between biological production and chemical precipitation that characterize this pivotal period in Earth's development. The beauty of these formations lies not just in their economic value or their scientific importance, but in their visual testimony to planetary transformation. The alternating bands of red and black, rust and silica, create patterns that resemble abstract art or musical notation, geological poetry written in the language of oxidation and deposition. Some formations reach thicknesses of thousands of meters, representing millions of years of continuous iron and oxygen interaction, layer upon layer of chemical collaboration between life and planet. Yet the process contains its own mystery, one that continues to puzzle researchers who study these ancient deposits. The banded nature of the formations suggests that oxygen production was not constant but cyclic, perhaps following seasonal patterns or responding to longer-term environmental changes. Some scientists propose that the bands reflect variations in the cyanobacterial populations themselves, periods of explosive growth followed by die-offs that reduced oxygen production. Others suggest that changes in ocean circulation or volcanic activity might have influenced the preservation of these chemical signatures. The truth likely involves all of these factors and more, a complex web of biological, chemical, and physical processes that created conditions unlike anything that exists in the modern world. The ancient oceans were chemical laboratories on a planetary scale, mixing dissolved metals with newly produced oxygen under atmospheric conditions that have not existed for billions of years. The banded iron formations are the laboratory notebooks of this great experiment, recording the results in mineral layers that will outlast the continents themselves. As the iron precipitation continues across the ocean basins, subtle changes begin to manifest in the chemistry of seawater itself. The removal of dissolved iron creates opportunities for other chemical reactions, other mineral formations that will characterize later periods of Earth's development. The ocean gradually transitions from an iron-rich, oxygen-poor environment to something more closely resembling the chemical composition of modern seawater, though that transition will require millions of additional years to complete. The bacterial mats continue their photosynthetic work, indifferent to the geological consequences of their metabolism. They have no awareness that their oxygen waste is fundamentally altering the mineral composition of their world, no understanding that they are creating the conditions that will eventually make their own anaerobic lifestyle obsolete in the surface waters of Earth. They simply photosynthesize, reproduce, and die, following the biological imperatives that evolution has embedded in their cellular machinery. The irony of their situation would be poetic if bacteria possessed the capacity for poetry. These microscopic organisms are engineering their own environmental transformation, gradually creating atmospheric conditions that will favor entirely different forms of life. The oxygen they produce as waste will eventually become the foundation of metabolisms far more energetically efficient than their own, enabling the evolution of complex life forms that will dominate the planet's future biology. Yet they continue their work with the mechanical precision of chemical reactions, unaware that they are writing the opening chapters of a story that will culminate in consciousness itself. The banded iron formations continue to accumulate on the seafloor, layer after layer of rust-red testimony to the ongoing atmospheric revolution. Each new deposit represents millions of oxygen molecules that have found their chemical partners and settled into stable mineral forms. Removing them from the active chemistry of the ocean system, the formations grow thicker and more extensive as the bacterial mats spread and multiply, creating an archive of planetary transformation that will preserve the memory of this period long after the bacteria themselves have evolved into entirely different forms of life. In the quiet depths where these deposits accumulate, far from the photosynthetic activity of the surface waters, the process unfolds with geological serenity. Particles of iron oxide drift downward through the water column like microscopic autumn leaves, settling onto the seafloor in patterns determined by current flows and chemical gradients. The accumulation is so gradual as to be imperceptible on any human timescale. Yet over geological time, it represents one of the most massive mineral precipitation events in planetary history, high above the iron-painted seafloors, where the ancient atmosphere meets the interface of water and sky. Methane molecules drift through air that has never known the touch of free oxygen. For 2 billion years, this greenhouse gas has wrapped Earth in a thermal blanket 30 times more effective than the carbon dioxide that will dominate later atmospheric chemistry. Methane concentrations hover at levels that would seem staggering to future atmospheric scientists, perhaps 1,000 times higher than the trace amounts that will characterize more recent geological periods. This invisible ocean of greenhouse molecules has kept the planet warm despite a sun that burns with only 4/5 of its eventual brightness. The methane originates from multiple sources across the primitive Earth system. Deep beneath the ocean floors, communities of anaerobic bacteria called methanogens transform organic matter into methane through metabolic pathways that require the complete absence of oxygen. These organisms thrive in the reducing conditions of sediment layers, hot springs, and hydrothermal vents, producing steady streams of methane that bubble up through the water column and escape into the atmosphere. Additional methane seeps from geological sources, volcanic outgassing, serpentinization reactions in the deep crust, and the slow decomposition of organic matter in oxygen-free environments. The atmospheric lifetime of each methane molecule stretches across centuries in this oxygen-free world, far longer than the decades that methane will persist once oxidizing conditions develop. Without oxygen to break it down through chemical reactions, methane accumulates in the atmosphere like water filling a bathtub with a blocked drain. Solar radiation provides the only significant destruction mechanism, slowly photodissociating methane molecules in the upper atmosphere through interactions with ultraviolet light. The process operates at a leisurely pace, allowing methane concentrations to build to levels that create a greenhouse effect powerful enough to maintain global temperatures suitable for life. But now, as oxygen molecules begin their ascent from the bacterial mats in the shallow seas, methane encounters its first significant chemical enemy. The two gases react with each other in a process that atmospheric chemists call oxidation, though the ancient atmosphere lacks the complex photochemical machinery that will characterize later methane destruction. Instead, the reaction proceeds through direct molecular collisions, oxygen atoms combining with methane to produce carbon dioxide and water vapor. The process is slow by human standards but rapid by geological measures, beginning the gradual dismantling of the methane greenhouse that has kept Earth warm for billions of years. Each methane molecule that encounters oxygen in this primordial chemical dance releases energy that dissipates as heat into the surrounding atmosphere. The reaction is exothermic, liberating the energy that was originally stored in the methane's chemical bonds and adding to the thermal budget of the atmospheric system. Yet despite this energy release, the net effect of methane destruction is atmospheric cooling, as carbon dioxide proves far less effective as a greenhouse gas than the methane it replaces. The chemistry operates with ironic efficiency, the very process that releases heat ultimately leads to global cooling. The transition from methane-dominated to carbon dioxide-dominated greenhouse warming unfolds with the glacial pace that characterizes all planetary atmospheric evolution. Individual reactions occur in microseconds, but the cumulative effect of trillions upon trillions of molecular encounters requires millions of years to manifest as measurable changes in atmospheric composition. The methane concentration begins its long decline from parts per million levels that will be toxic to most future life forms, dropping gradually toward the trace concentrations that will characterize Earth's later atmospheric chemistry. Scientists who study this ancient atmospheric revolution must read the evidence from chemical signatures preserved in rocks that formed during the transition period. Sulfur isotope ratios provide one of the most reliable indicators of atmospheric chemistry, recording the presence or absence of oxygen through subtle variations in the proportions of different sulfur atoms incorporated into ancient minerals. These isotope signatures suggest that the methane-oxygen reaction proceeded in fits and starts rather than as a steady progression, with periods of rapid atmospheric change alternating with longer intervals of relative chemical stability. The variability likely reflects the complex feedback mechanisms that connected atmospheric chemistry with biological productivity and geological processes. When oxygen production increased due to expanding cyanobacterial populations, methane destruction accelerated, cooling the atmosphere and potentially affecting the very conditions that supported bacterial growth. Cooler temperatures might slow biological activity, reducing oxygen production and allowing methane concentrations to recover partially. The system oscillated around changing equilibrium points as the balance of atmospheric gases shifted toward the oxygen-dominated chemistry that will characterize later Earth history. Regional variations in atmospheric chemistry add additional complexity to the global transition. Areas near major cyanobacterial populations experience higher oxygen concentrations and more rapid methane destruction, while regions distant from biological activity retain higher methane levels for longer periods. The result is a patchwork of atmospheric conditions across the planet, with some areas transitioning rapidly toward oxidizing chemistry, while others maintain reducing conditions for millions of additional years. The atmosphere becomes a mosaic of different chemical environments, each responding to local biological and geological influences at its own pace. The methane destruction process accelerates as oxygen concentrations continue to rise, creating a positive feedback mechanism that speeds the atmospheric transition. Higher oxygen levels lead to faster methane oxidation, which reduces the greenhouse warming that supports the warm conditions favorable to cyanobacterial growth. Yet paradoxically, cooler temperatures may also reduce the energy costs of photosynthesis, potentially allowing bacterial populations to expand even as their environment becomes less thermally optimal. The system balances on the edge of chemical chaos, with small changes in one component cascading through the entire atmospheric system. Modern atmospheric models struggle to fully capture the complexity of this ancient chemical transformation, partly because the initial conditions differ so dramatically from anything that exists in the contemporary world. The combination of high methane concentrations, rising oxygen levels, and minimal atmospheric mixing creates chemical gradients and reaction zones that have no modern analogues. Researchers must rely on laboratory experiments, theoretical calculations, and careful reading of the geological record to reconstruct the atmospheric chemistry of a world that no longer exists. The slow retreat of methane from Earth's atmosphere represents more than just a change in greenhouse gas concentrations. It marks the beginning of a fundamental shift in planetary energy balance, that will drive climate changes lasting for hundreds of millions of years. As methane concentrations decline, the effectiveness of Earth's atmospheric thermal blanket decreases, allowing more heat to escape to space despite the ongoing energy release from methane-oxygen reactions. The planet begins its gradual slide toward cooler conditions that will eventually culminate in the first global ice age in Earth's history. Yet the methane retreat proceeds so slowly that no individual bacterial mat or colony experiences dramatic environmental change. The atmospheric transformation unfolds across timescales that dwarf biological lifespans, allowing ecosystems to adapt gradually to changing chemical conditions. The cyanobacteria continue their photosynthetic work in waters that slowly become less methane-rich and more oxygen-saturated. Evolutionary time providing opportunities for genetic adaptation to the changing chemical environment. Only geological time reveals the magnitude of the transformation that these microscopic organisms are engineering through their collective metabolic activity. The interaction between methane and oxygen in the ancient atmosphere writes the opening chapters of a chemical story that will continue for billions of years. The same processes that begin during this pivotal period in Earth history, the oxidation of reduced gases, the cycling of carbon between different chemical forms, the complex interplay between biological activity and atmospheric chemistry will continue to shape planetary conditions long after the last methane molecules have been converted to carbon dioxide and water vapor. The ancient atmosphere becomes a laboratory for testing chemical relationships that will define Earth's environmental future. In the sunlit shallows where the ancient seafloor rises toward primitive shorelines, life begins to build its first monuments. These structures emerge not from conscious design, but from the simple mathematics of growth and death, as generations of cyanobacteria layer their lives into towers of limestone that will endure long after their builders have dissolved back into the sea. The formation starts small, mere bumps on the seafloor, where bacterial mats trap sediment particles and bind them with the sticky secretions of countless microscopic cells. But over centuries and millennia, these modest beginnings accumulate into towering columns that stretch toward the water's surface like underwater cathedrals built from biology and time. Geologists call these structures stromatolites, from Greek words meaning layered rock. Though the name fails to capture the elegant complexity of their formation, each stromatolite represents millions of years of bacterial growth, death, and calcification, as cyanobacterial communities follow the rhythms of day and night, season and storm, in their eternal pursuit of sunlight and carbon dioxide. During the day, when photosynthesis proceeds at maximum efficiency, the bacteria grow upward toward the light, their metabolic activity increasing the alkalinity of the surrounding water and promoting the precipitation of calcium carbonate from dissolved minerals. At night, when photosynthesis ceases, the bacterial communities rest, allowing sediment particles to settle into the spaces between cells and creating the fine layering that gives stromatolites their distinctive banded appearance. The construction process operates with the precision of biological engineering, though no engineer guides the work. Individual bacteria simply follow their cellular programming, photosynthesize when light is available, reproduce when resources permit, die when conditions become unfavorable. Yet their collective behavior creates structures of remarkable architectural sophistication, with complex internal geometries that channel water flow, optimize light exposure, and provide protection from environmental stresses. The stromatolites grow in columns, domes, and branching forms that depend on local conditions of water depth, current strength, and sediment supply. Modern stromatolites still grow in a few locations around the world, offering glimpses into the construction techniques that dominated shallow marine environments for billions of years. In Shark Bay, Australia, living stromatolites continue the ancient tradition of bacterial architecture, building limestone towers in waters too salty for most other life forms. These contemporary structures grow at rates measured in millimeters per year, providing a temporal framework for understanding the vast timescales required to construct the massive stromatolite formations that characterize the geological record of early Earth. The ancient stromatolites dwarf their modern counterparts in both size and abundance, reaching heights of several meters and extending across vast areas of shallow sea floor. Some formations cover hundreds of square kilometers, creating underwater forests of limestone pillars that represent the most extensive biological constructions in Earth's early history. These bacterial cities housed communities of millions of individual cyanobacteria, each contributing their microscopic portion to the collective architectural project that will outlast them by geological ages. The internal structure of these ancient monuments records the environmental conditions that prevailed during their construction. Seasonal variations in temperature, light availability, and storm activity created rhythmic patterns in the limestone layers, while longer-term climate changes left their signatures in shifts in growth rates and mineral composition. Scientists who study fossilized stromatolites can read these environmental records like tree rings, reconstructing ancient weather patterns and ecological conditions from the spacing and chemical composition of bacterial limestone. The stromatolites also serve as Earth's earliest libraries, preserving within their limestone layers the fossil remains of the bacteria that built them. These microfossils represent some of the oldest direct evidence of life on Earth. Cellular structures so well preserved that modern researchers can study their morphology and even analyze their chemical composition. The bacteria appear remarkably similar to their modern descendants, suggesting that the basic principles of cyanobacterial biology were established very early in Earth's history and have remained stable across billions of years of evolutionary time. Yet the stromatolite builders face a paradox that will ultimately limit their architectural ambitions. The very oxygen they produce as a waste product of photosynthesis gradually changes the chemistry of their environment in ways that will prove detrimental to stromatolite formation. Higher oxygen concentrations promote the evolution of grazing organisms that will feed on bacterial mats, preventing the stable growth conditions necessary for large stromatolite construction. The oxygen also changes ocean chemistry in ways that reduce the precipitation of calcium carbonate, making limestone formation less efficient and stromatolite growth more difficult. The irony emerges with geological patience. The most successful biological architects in Earth's early history are simultaneously engineering the environmental changes that will render their architectural techniques obsolete. The stromatolites grow larger and more abundant as cyanobacterial populations expand and oxygen production increases. Yet each additional oxygen molecule released into the ancient seas brings the stromatolite building era closer to its end. The bacteria cannot foresee this outcome, cannot adjust their metabolism to prevent the atmospheric changes that will transform their world. The chemical processes that enable stromatolite formation operate through the complex interplay between biological activity and inorganic precipitation. As cyanobacteria photosynthesize, they remove carbon dioxide from the surrounding water, increasing its pH and creating conditions favorable for calcium carbonate precipitation. The bacteria also produce organic compounds that serve as nucleation sites for mineral formation, encouraging the growth of limestone crystals within and around their cellular structures. This biogeochemical collaboration between life and mineral systems represents one of the earliest examples of what scientists call biomineralization, the biological control of mineral formation that will become increasingly sophisticated in later evolutionary periods. The stromatolite formations create their own microenvironments within the larger ocean system, generating chemical gradients and habitat niches that support diverse microbial communities. Different bacterial species colonize different zones within the stromatolite structure. Photosynthetic cyanobacteria dominating the sunlit upper surfaces, sulfur metabolizing bacteria thriving in the oxygen-depleted interior spaces, and various other microorganisms occupying specialized ecological roles within the limestone towers. These bacterial cities represent Earth's first complex ecosystems, multi-layered communities that demonstrate the potential for biological diversity even in the absence of multicellular organisms. The spatial distribution of ancient stromatolites provides insights into the geography and environmental conditions of early Earth. The formations cluster in shallow marine environments along the margins of primitive continents, suggesting that these areas provided optimal conditions for cyanobacterial growth and limestone precipitation. The absence of stromatolites from deeper water environments indicates that light limitation prevented photosynthetic activity beyond certain depths, while their scarcity in very shallow areas suggests that exposure to air or extreme temperature variations created unfavorable conditions for bacterial growth. Modern geologists use stromatolite distributions to reconstruct ancient sea levels, continental configurations, and climate patterns. The limestone towers serve as biological markers of past shoreline positions, while their internal structures record variations in environmental conditions that can be correlated with other geological evidence of climate change. Some stromatolite formations preserve evidence of ancient tidal cycles, with growth patterns that reflect the daily rise and fall of sea levels, in ways that provide information about the length of days and the distance to the moon billions of years in the past. The legacy of stromatolite construction extends far beyond the limestone monuments themselves. The oxygen produced by the cyanobacterial builders during millions of years of photosynthetic activity gradually accumulates in the atmosphere, setting the stage for the great atmospheric transformation that will define this period in Earth history. Each stromatolite represents not just a biological construction project, but a chemical factory producing the gas that will revolutionize planetary atmospheric composition. The towers of bacterial limestone stand as monuments to the beginning of Earth's transition from an anaerobic to an aerobic world, architectural achievements that mark the opening of a new chapter in planetary evolution. Above the limestone towers and bacterial cities, where ancient waters meet the alien sky, the very chemistry of the atmosphere begins its slow transformation from reducing to oxidizing conditions. This shift represents one of the most fundamental changes in planetary history. Yet it unfolds with such geological patience that individual bacterial communities experience only the subtlest variations in their chemical environment. The atmosphere that has existed for billions of years, rich in methane, hydrogen, and other reduced gases, gradually yields to a new composition dominated by oxygen and its chemical derivatives. The transition proceeds through mechanisms that atmospheric chemists can model but struggle to fully comprehend in their ancient context. Oxygen molecules rising from the photosynthetic bacterial mats encounter an atmosphere that has never known such chemistry, triggering cascade reactions that propagate through the entire gaseous envelope surrounding Earth. Each oxygen molecule acts as a chemical catalyst, enabling reactions that would have been impossible under the previous atmospheric conditions and establishing new equilibrium states between different chemical compounds. The transformation begins in the lowest layers of the atmosphere, where oxygen concentrations first reach significant levels due to their proximity to the biological sources in the shallow seas. Here, oxygen encounters methane, hydrogen sulfide, and other reduced gases that have dominated atmospheric chemistry for geological ages. The resulting reactions produce water vapor, carbon dioxide, and sulfur compounds that fundamentally alter the chemical balance of the atmospheric system. These reaction zones create gradients of chemical composition that extend from the surface waters to the upper reaches of the atmosphere. As oxygen concentrations continue to rise, the reaction zones expand both vertically and horizontally, creating a three-dimensional network of chemical transformation that gradually encompasses the entire atmospheric system. The process resembles the slow spread of a chemical fire through the gaseous envelope of the planet, though the reactions proceed at temperatures and pressures far removed from terrestrial combustion. Instead, the transformations occur through molecular collisions and photochemical processes that operate according to the fundamental laws of chemistry and physics. The atmospheric chemistry develops regional variations that reflect the uneven distribution of oxygen sources across the planet's surface. Areas above major stromatolite formations and extensive bacterial mat communities experience higher oxygen concentrations and more rapid chemical transformation, while regions distant from biological activity retain reducing conditions for longer periods. The result is a patchwork atmosphere with oxidizing zones expanding outward from biological centers like chemical shock waves propagating through a gaseous medium. Scientists who study this ancient atmospheric revolution must infer its progression from indirect evidence preserved in rocks that formed during the transition period. Sulfur isotope signatures provide some of the most reliable indicators of atmospheric redox conditions, recording the balance between oxidizing and reducing chemistry through subtle variations in the proportions of different sulfur atoms incorporated into sedimentary minerals. These isotopic records suggest that the atmospheric transformation was neither smooth nor uniform, but proceeded through a series of advances and retreats as the chemical system oscillated between different equilibrium states. The variability likely reflects complex feedback mechanisms linking atmospheric chemistry with biological productivity, climate conditions, and geological processes. Periods of rapid oxygen increase may have triggered environmental changes that reduce cyanobacterial activity, slowing oxygen production and allowing reducing conditions to reassert themselves temporarily. Alternatively, volcanic activity or other geological events may have introduced large quantities of reduced gases into the atmosphere, overwhelming the oxygen production capacity of biological systems and causing temporary reversals in the overall oxidizing trend. The chemical transformation of the atmosphere creates opportunities for entirely new types of mineral formation and weathering processes. Oxygen-rich conditions enable the formation of oxidized minerals that were impossible under previous atmospheric chemistry, while simultaneously destabilizing reduced minerals that have been stable for billions of years. The result is a fundamental reorganization of Earth's surface chemistry, with new mineral assemblages forming and old ones dissolving as the planet adjusts to its changing atmospheric composition. The weathering of continental rocks accelerates under oxidizing conditions, as oxygen attacks mineral structures that had been stable under the previous reducing atmosphere. This enhanced weathering releases new quantities of dissolved metals and other chemical species into the ocean system, providing additional raw materials for mineral precipitation and biological utilization. The increased chemical flux between continents and oceans creates new biogeochemical cycles that will characterize Earth's environmental system for billions of years into the future. Upper atmospheric chemistry undergoes particularly dramatic changes as oxygen molecules encounter solar radiation in the stratosphere and mesosphere. Ultraviolet light breaks oxygen molecules apart into individual atoms, which then recombine with other oxygen molecules to form ozone. This three-atom form of oxygen proves remarkably effective at absorbing ultraviolet radiation, creating Earth's first protective ozone layer. The formation of this ultraviolet shield represents one of the most important consequences of atmospheric oxygenation, as it will eventually enable the colonization of land surfaces by life forms that cannot tolerate high levels of solar radiation. The ozone formation process operates through photochemical mechanisms that require both oxygen molecules and specific wavelengths of solar radiation. In the ancient atmosphere, where oxygen concentrations remain far below modern levels, ozone formation proceeds slowly and creates only a thin protective layer. Yet even this minimal ozone concentration provides significantly more ultraviolet protection than existed under the previous oxygen-free atmospheric conditions, beginning the long process of making Earth's surface more hospitable to biological activity. The chemical complexity of the transforming atmosphere creates challenges for theoretical understanding that persist even with modern analytical tools. The combination of biological oxygen production, methane destruction, ozone formation, and enhanced rock weathering generates a web of chemical interactions that defies simple mathematical modeling. Each process influences the others through feedback mechanisms that operate on different timescales, from the rapid photochemical reactions in the upper atmosphere to the slow geological processes that cycle elements between rocks, water, and air. Contemporary atmospheric scientists use sophisticated computer models to simulate the ancient atmospheric transformation, but these models require assumptions about initial conditions, reaction rates, and biological productivity that introduce significant uncertainties into their predictions. The models generally agree that the transformation required millions of years to complete and proceeded through multiple stages of chemical reorganization, but they disagree about the specific pathways and timescales involved in the transition from reducing to oxidizing atmospheric chemistry. The atmospheric transformation also influences global climate patterns through mechanisms that extend far beyond the simple greenhouse effects of changing gas concentrations. The chemical reactions between oxygen and reduced gases release energy that affects atmospheric temperature profiles, while the formation of new types of clouds and aerosol particles alters the planet's radiation balance. These climatic effects interact with the ongoing changes in atmospheric composition to create a complex web of environmental feedbacks that shape the trajectory of planetary evolution. The shift from reducing to oxidizing atmospheric chemistry represents more than just a change in gas concentrations. It marks the emergence of Earth as a fundamentally different type of planet. The oxidizing atmosphere enables chemical processes and biological metabolisms that were impossible under previous conditions, while simultaneously making older processes obsolete or inefficient. The transformation establishes the chemical foundation for the evolution of complex life forms that will depend on oxygen for their survival, while creating conditions that prove toxic to many organisms that thrive